welcome. In this lecture, we are going to discuss about the behavioral simulation of counter-based DPWM with dead time using Xilinx ISE Simulator. So, this is a continuation of the previous lecture where we have discussed in detail about the counter-based DPWM and the Verilog-HDL programming. Then we are now going to do behavioral simulation and verifying timing parameter. In fact, in lecture number 66, we have introduced the live simulation, how to do Verilog simulation, Xilinx ISE Simulator, how to use Xilinx ISE Simulator and how to check the timing parameter. Okay, so those things we have discussed for a 4-bit ripple carry adder, but now we are going to check for this counter-based DPWM with dead time. So, here again we are not going to spend time because these things have been discussed in the previous lecture in detail. So, we have to make this block. So, our objective is to make this block, and this block is a submodule basically, or basically I will say this is a module. In Verilog it is basically it's a separate module. When you say submodule, it's a separate module as a part of main module. And the main module and all these things we will discuss in the subsequent lecture, in the next week lecture, but today we want to check how does the DPWM work and we have the timing diagram. So, again all this circuit we have explained in the previous lecture, Verilog code. I am not going to do that. The only thing, the output of the controller output, that will define our own, because we are not using any controller closed loop. So, it is a user defined for the time being to check. Again, this PWM switching clock we are not utilizing here, because we are not synchronizing, because it is just to check that whether we are able to generate the bit ratio, and using that PWM get signal Q PWM that we have defined, we are generating Q PWM signal, and after getting PWM, how does the QH and QL look like? That is the main objective in this particular lecture. Okay, so there are delay unit, we have discussed about all this detail, counter DPWM, and now for this case study and the dead time circuit also have discussed. So, what we have discussed now in this particular lecture, let us say counter we are using in which format. If you go back to the counter, so it is counter is use 4.8 format, but counter varies from what? We want the counter to vary from 0 to 499, that means it will go to the first bit of the integer and remaining 3 bit like 0. That means the counter will vary from 0 0 0 0 0 dot 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 0, and it can reach up to 0 0 0 1 1, maybe few internal bit we have to check which corresponds to 499, but it cannot go beyond that. So, if whatever is the corresponding number for 499. So, we have to choose this cont output which should be in between. That means, because the input to this block, if you go to this particular block, is a cont output. So, cont output originally is a 19-bit number, 4.15. That means, we are considering this cont output for testing purpose in the binary number. What are we going to take? It is in 4.19. So, we are going to take first 6 digit just for sake of 6 digit 0, then next 4 digit 1. So, 10 digit, then we still have 9, another 9 digit all 0, 5, 6, 7, 8, 9. So, this is just a number we are taking, maybe less, and this will give you what will be the duty ratio. And we have the resizing, that means when you resize, we are discarding, because we have to convert this into Q 4.8, that means we are discarding 7 bit. So, 1, 2, 3, 4, 5, 6, 7. So, anyway these bits are discarded. So, we are taking eventually when it will be resized, this data will look like this. Okay. So, that means we are taking, we have discussed the cont output, how much we are going to take. So, we will take this and let us go to our simulation. So, here I am showing just part of this lecture, because this is the overall voltage mode control which we are going to discuss in the subsequent lecture. Okay. And where we are going to do say we are going to program and we want to implement in the hardware using FPGA, but today we are only showing one part which consists of DPWM and Deadtime circuit that we have explained. So, we are only concerned about this circuit, and this Verilog code we have already explained in the previous lecture. Okay. So, it is like commented signal. So, we have discussed in the previous lecture. Now, what we are going to do? We want to do behavioral simulation. So, we select this, go to the simulation mode, we have to select this, and in the behavioral simulation, we have to first run this, because we are doing the behavioral simulation. It will check whether the code is fine or not. Then we have to click on the, so we must make sure that we are talking about this block, only the module that we are going to test in the timing diagram using simulator, Xilinx ISE Simulator. So, this is Xilinx ISE Simulator. Then simulate behavioral model. So, now we are opening this behavioral model. Now, we should remember in the simulation mode, which was not in hardware, we have to initialize the counter. It is not required in hardware, because hardware does not care about the initialization, because it is the counter is in a physical FPGA device which will always be 0, we cannot. But in the simulation mode we have to define 0, otherwise it will always set like a high impedance mode. So, that is why this line will only be applicable for simulation, but you can keep it for hardware, it will be ignored. So, then we have to set, so we discussed that what are we going to do. So, we have to select right click, force constant, and it is in binary number. So, what is the value that we are going to discuss? So, if you remember, we are going to talk about this number, that means first 6 digit 0, then 4 digit 1, all are 0. Okay. So, let us go back. So, first 6 digit 0, 1, 2, 3, 4, 5, 6, then 1, 2, 3, 4, then all 9 bit 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So, it will start from the beginning, or you can mention some starting time. So, let us say we are starting from maybe after 1 microsecond. Before that it was we have to check what value it will take by default, but we are forcing this value at 1 microsecond. So, we will apply here. Next, the clock, this is the clock which is very important. So, sorry, we should not make constant, we should use this as a force clock. So, leading edge is 1, then trailing edge is 0, and duty cycle is 50% and the time period is 10 nanosecond. So, this is what we need. FWF we are not using. So, we can simply set force constant, we can just make it 0. So, we are not using. Now, let us do simulation. So, let us simulate and check. So, we will stop here simulation. Okay. Now, let us go to the very beginning of this process. So, how does it look like? You see, we have defined the value of this control output at this point, because at I think we are somewhere around 100,000 nanosecond is the 1 microsecond. So, this is where we are going to set. What was the value that we have chosen? If you set resolution, so just a minute, controller output we have chosen what? I think we have taken 1 microsecond. Yeah. So, or it could be 2 microsecond, because we are setting the value. I think it was 2 microsecond, and it is coming 2000 nanosecond, that means 2 microsecond. Yes. So, after 2 microsecond the values have been stored in the controller output, and this is where we set. And if you check, if you come close, I just want to show that we have set what value? We have set 0, 0, 0, all first 6 bit 0, 4 bit 1, then remaining all 9 bit 0. And if you see the control output, it will resize, that means last 7 bit it has discarded the other bit. So, this is now Q 4.8 format, this was Q 4.15 format. And what about the counter? The counter is incrementing, that means if you go, you can see the counter is incrementing, this counter is incrementing, and it will reset whenever it will reach the 499 value. So, we will go to that point. Okay, let us go to the PWM signal, that means let us go to the PWM signal. So, let us go to the PWM signal. So, let us choose some here value. So, now you can see Q PWM is here, that means let us go here, we choose this some point here and let us zoom. You see, this is a point when the controller counter is getting reset, that means if you just go inside, I think PWM high, if you check the Q PWM, where is the Q PWM? Yeah. So, if I take it here and now try to take, so the counter is reset just before that, that means here. So, counter is reset and next cycle it will take action next cycle. So, Q PWM become high, because at this point the counter reaches 499 value. So, this corresponds to 499, then it becomes 0, and this 0 becoming 0, it is reset, and then the action is taking place, Q PWM is going high next cycle. So, this is 1 cycle delay. Once it goes high, Q PWM, so you can see the width is getting set, I mean whatever width we are setting, it is coming like this. Okay, so let us take this. Yeah. So, you see first that when Q PWM goes high, then the Q PWM delay is this. So, that means there is a delay. Let us go back very closely between this point. You can see that is delaying. How many cycle it is delaying? So, this is appearing here. So, 1, 2, 3, 4, I mean where Q PWM delay? It is here. So, in between how many? So, this is 1, 2, here. So, in between it is, so you can say 1, 2, 3, 4, 5. On 6 cycle it is coming. So, that is a 6 cycle delay, because I think we are using 0 to 5. Yeah. So, the delay is coming. So, this is a delayed signal. Then next part we want to see here. So, next part is that when Q PWM goes high and Q PWM delay is, there is delay. So, you can see the high side low side gate signal is getting off. So, this is a low side gate signal is turning off here. Okay, so, you just take this, the low side gate signal is turning off here, and this is what exactly we want, the low side gate is turning on, and the high side is getting high whenever the delay is coming. Now, you can take this cursor to this side to see what is happening. So, you can take it again whenever the low side signal, the Q PWM is going low, then first it is turning off the high side switch, and after some time the QL is on. So, that means we are able to generate the dead time circuit, and that will be used in the actual hardware. That means, if you go back to that. So, now you can change this value, that means we can take another extra 1. So, let us go back. So, if you want to again you can simulate, that means if you want to simulate once more, maybe you can close this, then go back to this, we are again doing this simulation, and now so we can change the value. So, let us say now we can fix the value force constant, maybe we can use 5 0 1 2 3 4 5, then 5 1 1 2 3 4 5, then all 9 0 1 2 3 4 5 6 7 8 9, apply, and then you set the QL to be force clock 1 0 10 nanosecond, and QPWM we are setting to be force constant to be 0. Now, if we simulate, so let us go back. So, you can take any arbitrary location here, because we want to check the simulation. You can check. Yeah, now you can see the PWM duty ratio has increased now. You can make it, you can further increase it. So, by that way we can adjust the duty ratio, and in the closed loop control this PWM duty ratio will be coming from the controller output. So, in summary we have discussed about this control output, the counter, and we have successfully validated our dead time circuit, and we have discussed this code, and we have discussed how to check, because this is the first step for doing Verilog. Slowly we are going to implement voltage mode and current mode control, and I will show you some more live demonstration of this digital voltage mode control, but the code will be discussed, the overall code, in the subsequent class. So, all these things we have discussed, dead time circuit we have discussed. So, how to generate this delay block, these things are also discussed. So, in summary we have discussed the counter based DPWM Verilog-HDL coding. We have made behavioral simulation, and we have successfully tested, verified the timing parameters. Now, we are ready to move for the next step, which will be coming in the next week, that how to implement digital voltage mode and digital current mode control, how to implement PID controller, PI controller, and how to successfully test it and dump it into the FPGA, and how to get the hardware result, and how to implement all these control strategies. That is it for today. Thank you very much.